Okay, so today we are going to move on to another kind of optimization we call evolutionary optimization. Okay, so the most famous method in evolutionary optimization is genetic algorithm. Since you are already preparing your project, probably you have seen some of the papers or some reference which is using GA. Okay, so today I'm going to show you what is GA about. Okay, so usually GA is utilized for discrete problems. Okay, why discrete? Why can we use what we have learned to handle discrete? So think about this. If I'm solving a problem, minimizing some kind of f of x, and maybe I have some constraint. Okay, however, x has to be integer. Okay, so if x has to be integer in this problem, then you cannot take derivative. Okay, so if you cannot take derivative, you cannot use gradient-based approach. That's why for discrete problems, you cannot use what we have learned. Okay? And since for some problems, if your design variable is discrete, the number of variables become fewer. You may have fewer possible solutions. Okay? So if that is happening, let me also give you one example. Let's say x has to be integer, and x ranges from, for example, from 2 to 10. If that's the case, then x equals to 2 or 3 or 4 or until 10. So there are only how many? Well, from 1 to 10 is 10. So 2 to 10 is 9. There are only 9 possible solutions. So if you are solving such a simple problem, only 9 possible solutions, sometimes you don't need to do optimization. Just try all 9 solutions. Pick up the best. If you remind yourself, think about what you have learned in gradient-based approach. You have to plug into the functions multiple times during the optimization. So the amount of function call usually is not that small. It's like usually you need to evaluate the function maybe 50 times, 100 times, right? So if you can only try 9 times to figure out what is the solution, in this case, just try 9 of them. Okay, so whenever you define a problem and you try to solve the problem, try to find the optimal, always think about the size of your solution set. Possible solution set. If the size of the solution set is quite small, maybe you don't need optimization. You just need to try every solution. Then the best one is the best. Okay? So today I'm going to introduce GA. For GA, usually it's handling a pretty large solution set. So you need some kind of strategy to find the optimal. Okay? So GA usually handles a pretty big solution set. So GA will use this unique way to try to find the optimal solution. And also it has the potential to find the global optimal. Has potential of finding the global optimal. Okay? For gradient base, it doesn't guarantee global. So gradient based approach is only good for continuous problem. And it has to be convex. Good for convex. And only good for local optimal. What do you mean by convex? Let me remind you what is convex. If I have a problem, looks like this. If this is X, this is F. Okay? If your starting point is right here, this should be your global optimal, right? And these two are local minimum. So for local search, gradient base is a local search kind of method. It usually ends up with a local optimal. So sometimes if you are not lucky, your solution doesn't jump into the area with the global. So gradient-based approach is nice, it's precise, but it doesn't guarantee global optimal. Okay, so what is convex? If a function is like this is convex. If a function is like this, meaning if you move left or right, it goes to two different minimum, then it's concave. Concave, okay? For 2D problems, this is for 1D. If you have a 2D problem, if you try to view on the top, and if you have a design space, for example, maybe some kind of linear programming problem, and you have a closed boundary of your solution set, this is convex. Okay? And if you have a region that looks like this, then it's concave. Because if you take a walk from one point to another point inside the solution set. Along this walk, all the points stays inside of your solution set. Then we call it convex. But if you try this one, if you try to walk along this path, your solution was inside a feasible space, but during the walk, you jump out of the feasible space. Then you jump back. So in this kind of space, it's concave. So gradient-based approach cannot guarantee to find optimal for concave design space. Okay, this is talking about the shape of the solution set, and also on the top, it's about the shape of the objective function. They are quite different concept, but they both need to have this kind of convexity, so you can use gradient-based approach properly. Okay, now if you use GA, GA doesn't worry about these. GA can handle all these problems. Okay, let me introduce you why GA can handle this. So there are some terminologies inside GA. It's trying to mimic the evolution of some kind of species, some kind of animal or whatever species. So for thousands of years, you have a single cell. Thousands of years ago, you have a beginning of single cells, and then multi cells, and then you have simpler creatures. Then the DNA evolution, you have dinosaur, and then dinosaur cannot handle some disaster, so some other species stay alive, some other species died. So GA is kind of trying to follow this kind of concept. It allows the random design to evolve by some kind of rule. And if this evolution creates a better species, better design will survive, weaker design will die. Okay, so it's a kind of a story like that. So later on, we are going to do multiple iterations. So in GA, so here is, I'm starting to talk about GA. For the iteration in GA, we call generation. So it's like this generation in this generation, human exists, and maybe hundreds of thousands of years later, there is a superhuman or some kind of creature dominate the earth. So far, human is dominating the earth, right? But in the past, some other creature is dominating. So in every generation, different kind of species are dominating. So GA treat one generation as one iteration. Okay, so in each generation, there will be multiple random designs. So this is like random species. Okay, and number of random design. We call population. Okay, so it's like if I take some numbers as an example, maybe my max generation equals to 500. So it's like in GA, I allow the species to evolve for 500 generations. So it's like 500 iterations. And for each generation, I am going to randomly generate different kinds of design, or in the story of genetic analysis, random kind of species. So I can say I can have, for in every generation, my population equals to 50. Okay, so it's like there are 50 different kinds of animals, or different kinds of species, or different kinds of human-like, or human. Okay, so maybe there are like a European, Asian, so maybe there are 50 different kinds of human. Okay, something like that. But how are we going to have 50 different designs? So this is going to be randomly generated. Okay, so later on, at the beginning of every generation, we're going to randomly generate 50 random designs, and then we're starting to follow the GA procedure to allow some kind of competition between them. And then the winner will survive this generation. His DNA will evolve to the next generation. And in the next generation, the best one, the best DNA stays there. Okay, something like that. Okay, so for each random design, we use some kind of concept, just like a DNA, to encode that design. So we call that, for each random design, we use something called chromosome to encode the design. Usually, chromosome is following the binary encoding. Okay, usually that's the way. Okay, so I can give you one example. If I again try to minimize some kind of function x1 and x2, and then I may have several constraints. But here, my x1 is smaller than some upper bound and lower bound, larger than some upper bound, lower than some upper bound, so is x2. So in this case, I can start to make a decision. I'm gonna use the binary encoding to decide the values of x1 and x2. Okay, so let's say my chromosome has 8 digits. So the first 4 and the last 4 will be utilized to represent the value of x1 and x2. And because they are binary, so the possible binary codes starts with 4 zeros, 0001, 0010. So this is binary until the last one is 1111, right? So how many possible combinations are there? So basically, there are 2 to the 4th possible combination for value of x1, right? Because for each digit, it's either 0 or 1. So the total possible combination would be 2 to the power of 4. Okay? So that means 16. 16 possible combination. So what you can do is, if this is the range of your x1, let's say this is x1 lower bar, x1 upper bar, and this is the value of x1, you can cut this interval into 16 different positions. So you can have 16 of them, of points. You can then map, maybe this one is your 0, 0, 0, 0. This one would be your 1, 1, 1, 1. And the second one could be your 0, 0, 0, 1. You can try to find some kind of mapping, linear mapping, between the digits and the true value. When you do that, your design space becomes discrete. You can only find solution inside this discrete points from this interval. Okay? So for the entire design problem, now how many possible solutions are there? Totally, 2 to the power to the 8th possible solutions. So that would be how many times? 2, 5, 6. So if you design the problem in this way, the total possible number of solutions will be 256 times. So you, of course, you can try all of the 256 points. One of them would be the solution. Okay? But the idea is not to explore the entire design space. When you design a problem like this, your design space basically would be the 556 points. Okay? The goal is not to explore every possible solution. Okay? And usually, in this simple example, we have 8 bits for the chromosome. Sometimes when you are solving a complex problem, the length of the chromosome could be very long, like more than hundreds. So if you have, let's say, 100 digits, then the possible solution would be 2 to the power of 100. In that case, the possible solutions are so many. It's impossible for you to try all of them. Okay? So that's why later on, we are going to use a GA strategy to pick up the solutions. Okay? Now you understand how you can design the chromosome. You can design the chromosome in any way, as long as they are binary encoded. Okay? So next, you need to understand one thing. That is fitness value. Fitness. Okay? So usually there are many ways to do GA. So I'm gonna tell you what's the, maybe I tell you the solution process first. So first, you have population generation, meaning you have n random designs. Okay? And usually what you need to do next is to do feasibility check. So remove the chromosome that does not satisfy feasibility. Usually you can do that right here. Because for GA, usually you don't want to handle infeasible design. So if your example is right there, here, G smaller than 0, and that would be your feasibility check. For the variable bounds, because the way you design the chromosome, automatically the random solution, random chromosome is within the variable bound, right? So in this particular example, I just need to check if the design satisfies G smaller than 0. Okay, usually you do feasibility check here. Then you will evaluate fitness value. So usually, what is the fitness value? Usually it's like a score related to objective function. So sometimes you're minimizing, sometimes you're maximizing. You can say you want the fitness to be larger the better, or smaller the better. If you want to map your function value to a scoring system called fitness, if you like the score of 0 to 100, or if you like the score of 0 to 1, or you just like the function value as your fitness value, that's all of them are fine. Okay? But later on, the way you define fitness will affect some of the process, the next step. So, of course, if you define the fitness value properly, that may help you find the solution more easily. Okay, so fitness. Basically, it's a quantitative score that depends on the objective function value of that design. Usually next is the step called selection. So the goal of the selection process is to pick up the one that is good. So it's like you have 10 children, you want to see which one does the best in racing. This kid runs the fastest. So it's like how fast your children run is the way you score them in fitness process. And selection is like, okay, my youngest kid runs the fastest. That's the fastest runner. Okay? So usually selection, the way you select depends on the fitness score. Usually it's like that. But in this process, you still need some kind of randomness. Even one of the chromosome, one of the design that may not perform well, but that doesn't mean it's a bad design. Or maybe it's a bad design, but that doesn't mean we should just ignore how the design look like. So usually selection process depends on fitness, yes, but also keep some designs with some random process. So you kind of randomly pick up some chromosome from the population, but you also kind of want to pick up the good one, but you don't want to just ignore the bad ones. Okay? So that would be the goal of the selection process. Next, usually is the process we call crossover. So crossover means you have two chromosomes, and you allow them to exchange their design parameter. So it's like an exchange their DNA. Okay? So allowing two designs to exchange some part of their chromosomes. Yeah. But it's not like every two crossover. No. It's also just giving them a chance to make some exchanges. Okay? And another procedure is called mutation. So mutation allows each design to switch some of their chromosome from 0 to 1 or from 1 to 0. So mutate is like maybe some radiation hit you, so your DNA kind of changed. So how do you change your DNA? In this process, we have 0 and 1 chromosomes. If one of the bit originally is 0, if it changes to 1, that has been mutated. Okay, so mutation is like that. After this, what do? Usually, you end up with same amount of designs. So keep in mind, we have n random designs here. Okay, even after selection, we still want to make sure there are n designs. Because even with selection, we want to pick up the same amount. So the size of our design in each generation remains the same. Okay? And even if, right here, I forgot to mention, for the feasibility check, sometimes some design fail the feasibility check. So what would you do if some design fail? You can always go back to population generation and generate more design until you have n feasible designs. So the goal is to have n feasible designs here after feasibility check. So here regenerate only if you have infeasible. Right? So idea is like that. If you have infeasible design, you can regenerate. Okay? So from the feasibility check, you should send n feasible designs. After finish, you compare how good they are. In selection, you kind of pick up several good designs and keeping some bad designs. You allow them to cross over, so two DNAs, the two chromosomes line up, some part of their body swapping, they exchange their body. That doesn't change the amount of designs. We still have n designs, right? Mutation, 50 chromosomes, some of them has digit mutation, 0 to 1 or 1 to 0, still we have n designs. At the end, we should still have n designs. But those n designs may be completely different from what you had earlier. Because at the beginning, you have n random designs, but at the end, after selection, crossover, mutation, maybe all of them changed. Okay? So since they may be changed to a different design, here we will do feasibility check again. But if here some design fail, you don't regenerate here. If here you found some design is not feasible, then it's not feasible. And here you also check their fitness value. Okay? So after here you found 15 new designs and you check how good they are. Is it not charging? Hold on. Forget to turn on power. Okay, okay. Now it's charging. Okay. Sorry. It was not charging. So after you do the finish check, maybe you have less than n designs because some of them are not feasible. That's fine. Okay? And after the final fitness check, usually what you do is you keep the good ones. So you will move on to the next generation. Okay? So after the final fitness check, here, you move on to next generation, but usually keeping one or more we call elite chromosome. So elite is the best out of selection, crossover, mutation, feasibility check, out of everything. The super species, super design in this generation. You keep them. You move on to the very top. That's your next generation. Basically, second iteration. So originally, you need to randomly generate n design. Since you keep some elite chromosome from the previous. So here, you don't need to generate the same amount. Let's say you keep one best design from the past. So here in the next iteration, you just randomly generate n minus 1 design. Okay, so that would be the general process of GA. If you start to read some papers or some reference, you may see some of the GA perform in a different way. Sometimes they do not do feasibility check. Sometimes they keep the elite before selection or after selection. Or sometimes they don't mutate. Or sometimes at the end, they don't do feasibility check. So there are many different versions. So it's a very open procedure. You can try to do what you want to do. Okay, so I think the key is that you must understand how GA works, and if something happened, you should be able to figure out what went wrong. Then you can go back to your procedure, try some other settings, some other steps, some other procedures, and see if that makes better sense for your problem. Okay? Now I'm going to talk about the details of selection, crossover, and mutation. So those are the three key procedures here. I never talk about the details of those three. So let me let you know about the details. So let's talk about selection. So for the selection, usually what I work on is called the Russian roulette. Russian roulette. So what is a Russian roulette? You know, you must know in some of the movies, they have a gun and the gun has 6 bullet holes. You only put 1 bullet inside the gun, and then people take turns to fire the gun and see who dies. So it's a Russian roulette. Okay? So Russian roulette basically is a kind of procedure with randomness. Okay? So, but it's not like it. Right here is not like we put a bullet. It's just conceptually. It's called the Russian roulette or roulette selection. So, let's say after the fitness check, let's say you have N chromosome with N different fitness values. So maybe I can call them Fi fitness values. So basically I goes from 1 to N. Okay? So after feasibility check, fitness value, each design should have a fitness value, right? So let's say in this particular design, Fi larger the better. Okay, you design your fitness in such a way, Fi larger is a better design. So you can now do something. You can define a selection probability. You can do something like this. So you sum all the fitness value together and use the ith fitness divided by the sum of fitness. So what you end up with is something like this. Conceptually, it's like a roulette. And you cut the roulette into multiple areas. But they are getting smaller and smaller. The last one is very small. So let's say it's like a wheel that's being separated into n different areas. So conceptually, it's like the angle defined it by pi. So if you have a larger fitness, that design occupy a larger portion of the angle in this wheel, because it's a better design. So I give the better design a larger piece. And if I have a bad design, the probability of being selected is very small. So I give the bad design a small portion of the angle. Next, I'm going to use random generation. In computer codes, what you can do is to use, you need to be careful, this has to be normally distributed. Not normally, uniformly distributed. So you use a uniform random generation, and you can generate a value from 0 to 1. Okay? So let's say 0.2. And you can map the angle from here originally it's 360 degree. You can map to which degree you have, or like which position. Map to the 360 degree of the wheel. So if you do that, then this uniform random generator will fall into some position inside the wheel, and because the design with the highest fitness occupy a larger space, so the probability of picking up that particular design is higher. And you are going to do this n times, repeat n times. So it's very possible that at the end you will have repeated design, because the good ones, it has a larger probability to be selected. It's very possible you select the same design twice or more. It's okay. So please be aware that it's okay to select the same design multiple times. Why do we allow this happen? Why do we select the same design multiple times? Because later on we have crossover and mutation. If we think, so it's like if you have 10 children, this one of your kid is doing a better job. I hope I can have duplicates of that kid. So biologically, I'm duplicating that kid. So I will keep better genes in the generation. I don't even want to pick up the bad children. Okay, something like that. Okay? So we want to keep the chromosome, it's like a DNA, right? The chromosome, we want to keep the good ones. We even like to have more of them in the population. Okay, so that's one way to do selection. This is not the only way. There are so many different ways. Okay? And when people define the selection probability, there are also multiple ways. So it's very, you can try to figure out how you want to do selection. Some researcher doesn't even do selection. When they randomly generate, they give equal probability to all random design. They directly move on to crossover or mutation. That's also one approach. Okay? But in my experience, if you keep the good ones, giving them better chances to survive, the good ones can move on to the next generation. So this is what I'm looking for. Okay? So this is selection. Okay? The next one is crossover. So for crossover, it's like this. I put two chromosomes together. So maybe this is my I-th chromosome, this is my J-th chromosome. Okay? And I will have some kind of how do you call that? Encoding, we call pointer, right? This is a pointer. So the pointer will move on to the next position. Next position. The pointer moves on from the first digit to the last digit. Okay? And every time the pointer moves, you can have a random number being generated. So here you have, again, uniform random value generated. So it ranges from 0 to 1, right? And then you can define something called crossover rate. So you need to define crossover rate. Usually, it's not very small, but cannot be too large. Let's say 30%. So it's like every time I check, I give this opportunity to have a 30% of the rate to cross over. So once I randomly generate value from 0 to 1, I can say if this random number smaller than my crossover rate, 30%, then crossover at this bit, something like that. Okay, so or you can decide, because you can actually define the pointer at the gap between bits. Maybe that makes more sense. So the last position would be right here. So it's like you are looking for the position you cut the chromosome into half. So here I won't say at this bit, I will say at this position. So if the randomly generated number is not smaller than your crossover rate, else move on to next pointer position and repeat this process until it goes through every possible position. So let's say right here, right at this green arrow position, we found a random generated number that is within the crossover rate. Then what do? I will swap the body right at this point, right at that position. So it's like, okay, I cut my leg, swap with the other person's leg. So maybe it's like we are designing chromosomes that generate superhuman. We want the superhuman to be strong and being able to run fast. And we found that, this person's gene is having a strong upper body but weak lower body. The other gene has a strong lower body but weak upper body. So they are both not excellent. But by random process, maybe someday, this particular strong upper body can be swapped and combined together with a strong lower body of some other chromosome. Then we generate superhuman, something like that. Okay? So all these are based on random process. But why does GA does this? Now let's think about what's gonna happen if GA is doing this. So earlier we mentioned our GA, the first part is x1, second part is x2, right? So these are just like two different design points. So in the design space, there are just two different design points. So this is your ith design, this is your jth design. So if one day the random generator asks us to do the crossover on this ith and jth design, and if we have the position for crossover right at the middle between x1 and x2, what's happening is the x1 value of your ith design will move to here, because your x1 value remains the same, but your x2 value will be your jth design. And for the jth design, your x1 value remains the same, but your x2 value goes to the other one. So it's gonna be something like this, right? If you think about it, if the crossover position is right there, and right in the middle, you're basically just swapping some part of your design. Okay? Let's take a look at another example. If this is your x1, x2, this is your ith design, and maybe one day the cutting point is right there. Okay? So maybe for the other design, let's say you originally have 0, 0 here, and this guy has 1, 1. So what's happening is your x2 originally has a smaller third bit and a fourth bit. After swapping, you have a slightly larger third bit and fourth bit. So it's a small increment on x2. So if this is happening, then your ith design move a little bit, increase a little bit, right? But x1 remains the same. So crossover kind of guides you to change the value of your design following some kind of pattern, but the pattern came from some other design. Okay? So that's what happened. Sometimes it's just a movement along the x, sometimes it's movement along the y. And sometimes the movement is small, sometimes the movement is large. So, unlike gradient-based approach, crossover and mutation in GA has the ability of making small changes, but sometimes huge changes. So in the design space, you may see your design point jump around or slightly move around in some local. So it has the ability to move a little bit in the local or jump to some other area. That's why GA has the ability to find global optimal, because it has the ability to jump around. And also possible local search. So it combines the advantage of local search and also global jump. But it requires a lot of random process. So usually it takes a lot of random trials. So GA usually takes more effort than gradient-based approach. if one problem I need 100 function calls using gradient base, maybe using GA I need 10 times more function calls. Okay? But we know if we use GA, we are already using fewer function calls than the complete solution set. Because if your GA is having 100 digits, then the possible solution is 2 to the power of 100. So that's a huge solution set. Okay? Next one would be mutation. Mutation is similar to crossover, but only work on individual chromosome. But for mutation, I would suggest you to handle the pointer on the bits. Move from bit to bit. And every time, check random value. See if it's smaller than your mutation rate. So usually mutation rate is not very large, because for the mutation, it could be a dramatic change. So usually, for example, 10% or even lower. Sometimes 5%. You don't want to have too many mutations, because mutation really generate a huge randomness. So if yes, your random value that is within the mutation rate value, if yes, then 0 change to 1 or 1 change to 0. If no, then move on to next bit. So the pointer move from one bit to the last bit, just to check whether this chromosome needs mutation. Okay? Okay, 1, 2. Okay, that's pretty much it. Okay, I think we can now move on to coding. I will solve an engineering problem in MATLAB and show you how it look like. Okay, so let me turn this off. Let's now start from scratch. Let me go to the okay. Let me create a new code. So again, start with clear CLC, close all, and I'm going to solve very simple problem. So I'm gonna use symbolic so I can do plotting more easily. So sims x1 and x2. Okay, and then I can have objective function. Let's say or we can use some of our old problems. Yeah. Let's just solve the same problem. Here, this is good. Earlier we used fmin_con, right? Let me try to solve this again. F min count, remind ourselves what the problem looked like. Okay, so this was F min count. The solution was here. No, was here because there is an equality. Not solved yet. Because this time I am video recording the screen, so it's taking some time. Over here you can see that's the optimal. You have to find a point on the green curve, but also in the feasible space bounded by the two blue lines. Okay. Actually, if I shrink the plotting zone to 0 to 5, you can see everything more clearly. You can see how F min count finds the point intersection between the green curve and the blue straight line. So let's try to use GA to solve for this. I want to make the radius larger, so maybe 4. Yeah. If this is a problem, then the solution is more obvious. Forget to modify here. 4. Okay. Do it again. So this is F min count. Okay, this is a procedure of F min count. Let's try to see how GA handles this. So the problem is here. I'm gonna copy the whole thing to my GA code. Okay. So now I'm gonna say gen means generation. Starts from 1, and I need population. I'm gonna call it pop. Let me say 10. So I need 10 random points every generation. Okay. So here I'm gonna say max generation is 100. Okay. So what's next? I need to define chromosome. So I decide to use so here chromosome generation. Okay, so for I goes from 1 to pop, because I have 10 designs, 10 population. So for each design, I need to go through some coding, and I'm gonna use let's say bit for X. Let's say 8 bits. Okay, I'm gonna use 8 bits for X. So in this case, I need totally 16 bits. Because for each X, I have 8 bits. So I'm gonna call my chromosome chrome. Okay, chrome. And for there are a bunch of 0 and 1s. So I'm gonna use I, comma, and the rest equals to I want to use uniformly generation. So rand. Rand is a uniformly random generator. And I'm gonna say 1 comma 2 times bit for x. So this will give me a bunch of numbers ranging from 0 to 1. So I'm gonna round these number values. If I don't do this, let me show you. Rand 1 comma 16. That's going to give me 16 random numbers uniformly distributed inside 0 and 1. But they are not 0 and 1. They are like with digits. So I'm gonna round this. Just do a rounding. So after rounding, it will become either 0 or 1. So they will become 16 0 or 1s. Okay? Then I will do this for number of populations. Okay? So actually, this way of coding is not effective. I can just say, so this is one way of coding using a for loop, but you don't really need to do this. You can just say chrome equals to all these, but here pop. That's just one line. So it's a random matrix. You have 10 rows, 16 columns. So it's like this. So each row is 1 chromosome. So I have 16 columns. Okay, so one line you can generate 10 designs, right? So this one I just hide for you. If in the future you want the code to be running gradually, then you can figure out from the original code. Now I need to do feasibility check, but I need to map those. I need to map chromosome back to X. How do I map it? Then I need again I use a for loop. For 1 goes 1 to pop. So I have the chromosome already, right? I will for the first 8 bits, this is going to represent my X1. Okay, so there should be something called binary to decimal. Yes, binary to decimal. If I try let me double check how the binary to decimal works. Or we can write our own binary to decimal. I need to. We need internet. Hold on. Okay, so right here you have binary to decimal. Okay, we can see, okay, binary string. So binary to decimal actually needs an input of a string of 0 and 1. So what do? If I say number to string and a matrix of 0, 0, 1, what's gonna happen? It ends up with a string of 0 and 1s. Okay, so I can say number to string converts the chromosome, the ith row, and the first half, so 1 to bit for x. If I do that, I convert 8 0 and 1s into a string. So let me show you. I should let me save this. Let me call this GA. Okay. Let me call this code GA. Okay. If I run the code up to here, so here, this is my chromosome, right? And if I say, if I use this code and first row, so first chromosome, and first 1 to 8, it will give me a string of 0 and 1. But if I say binary to decimal, it will decode this value, this binary string into decimal. Okay, so right here, binary to decimal. Okay, so what would be the largest possible code? The largest would be 255. Smallest will be 0. Okay, so we can linear map the decimal value from 0 to 255, totally 256. Map it back to the range of x1. Okay, so here, how do I map it? So I should compute for the largest decimal value for my, so later on it's easier for me. So max decimal would be this, but here once bit for, okay, you can turn off now. So I generate 8 ones, and I just directly use binary to decimal. So I know this will be 255, right? This will be 255. So one line, I know the possible maximum value for my decimal is 255. So over here, if minimum is always 0. So this divided by the max value, then it's the percentage inside the range from 0 to 5. So I just need to multiply. Zone is my boundary, right? So zone 2 minus zone 1 okay, so that should be my x value. When it's 0, then it's 0. When it's 1, it will be 5. Right? That's the mapping. 255. 0 to 255. 0 to 255. Yes. Okay? So this will be my x1. So I will say, I will call this x1 or the chromosomes x1, but the ith design. A chromosome, let me call chromosome X. So this will be my ith first. That means x1 for the ith chromosome. So if I do the same thing, this is too long. Hold on. Let me move this to the second line. Okay. Wait. Hold on. Oh, no. Too many. Just this. Yes. Okay. Okay. So I will do the same thing for x2. But for the x2, here you will be bit for x plus I. No. Here. Bit for x plus 1. So from the 8th one to the 2 times bit for x. 8 to the 16. Okay? Let's try this. Let's run the code. So chromosome for chrom X. Oh, I had a typo. Sorry. Chrom X. Okay, run it. So chrom X, it ends up with 10 different design points. You can see they are all within the range of 0 to 5 because my design space is within 0 to 5. I have something is wrong. This should be 4 and 3. So if I change the design space, if my zone is not 0 to 5, it's 0 to 100 for x2. Let's see what's going to happen. You can see my x2 ranges from 0 to 100. Right? So with this general coding, I just need to modify here. Zone means my design space, upper bound and lower bound. The rest of the coding will just do it for you. Okay? Okay. Good. So after I map the points back to the design space, I need to do feasibility check. I want to see whether those points satisfy the constraint. If not, I will eliminate that particular design. So again, another for loop. So in fact, all these can be written inside a big for loop. I intentionally separate them into different loops so you can just or should I just write them in a big loop? Yeah, let me do that. Maybe that's better. So in that case, I will keep this loop. So I will not use this one. I will not use the big one. I will just use the loop. If that's the case, this should be written inside here. Okay, and then mapping back. I don't need this, and this whole thing moves to here. Okay. Feasibility check. Okay. So it's everything is within this big. No. It's too many for loop. Just one big for loop, like this. Okay. Chromosome generation, map to X, and then feasibility check. So what do we do? Let's give a so initially let's create some kind of flag. So feasible flag. And let's say initially they are all invisible. So let's say zeros. And 1 to number of population. Yes. Okay. This should be made outside. For each population. Oh, then I just need. Do I need to? Okay, sorry. I will just do it outside. So feasible flag equals to 0 means not feasible. Okay. So if I generate an invisible design, I will go back and repeat. Okay. Okay. So how do I check? So I now have the X values. I just plug in. See if that satisfies. So here, a for loop, J goes 1 to the length of G. G function, yeah. And then I will just if substitute. Actually, I'm gonna plug in one by one. So yeah, if substitute into G function, and then x1 and x2, and my current value. So current value would be this one. If you plug in that is larger than 0, then let's say smaller than 0, then it's feasible. So the feasible Let's initially say it's feasible. So when it's larger, it's infeasible. So I will switch this flag to 0. Right? So I will go through every constraint, plug in my design point to that constraint. If that constraint value is larger than 0, it's invisible. So I will change that feasible flag from 1 to 0. Okay? So if there's one constraint that is being violated, the flag at the end will be 0. And also, I need to go through all the equality constraint as well. But for equality constraint, it's very challenging for GA because we discretize our design space. So our design points are actually on the grid. So maybe very few points lies on the equality constraint. Maybe none of them lies on it. If you plug into equality constraint, maybe none of them equals to 0. So you need to allow some kind of error. So here, I plug in, here I should say G and the jth one. Yeah. Here, H, jth one. H I only have one. So in this problem, I only have one, or I should write it in a cell as well. So later on, if I have multiple H, then this code still work. So after I plug in, that would be my function value for H, but it's only satisfied if it's equals to 0. So now I would say larger than some small allowable value, let's say 0.1. If it's larger than 0.1, I will treat it as infeasible. So if the equality value is within 0.1, I treat it as feasible. So on that green curve, there will be a error band. So our solution won't be exactly accurate. Okay? So let's try to see what's happening. Let's pause right here. Okay? So our first design is not feasible. The flag should be inside the loop. Okay. Let's run again. First design, not feasible. Second design. Let's just plot. Just show the feasibility result on the dialog. None of them are feasible. Maybe it's because of the equality constraint. So it will be very. So what do we do? In our case, if it's not feasible, we need to regenerate the design. So over here, I will say if this particular design is infeasible, I need to regenerate. So how do I regenerate? You know, for the for loop, when it goes to the bottom and move back, the index increased by 1. So what I can do is to decrease the index by 1. So that particular design will be regenerated. Okay? So, but if I do that, if it never generates feasible design, it will be an endless loop. So let's try this. Okay, let's see. Okay, so maybe we plot this. Let's use the coding for plotting. This is plotting. Okay, let's plot out. This is for plotting. H. And let's try to plot all the. So right now, if not feasible, my index, the I index will decrease by 1. So it will repeat the process. So if else means it is feasible. If it is a feasible point, I will plot the position, plot out the position of that feasible point. So let me plot the point. Plot the point I can use here. And plot the. So that particular point would be this one. No need to pause and draw now. Let's use black color. Okay, show it. Huh. Okay. There are only two. Maybe let me try more. Where are they? No. Even for the for loop, even I minus 1, it doesn't. Then I should use a while loop. While I is smaller than pop, I do this. So if infeasible, I do nothing. But if feasible, then I equals to I plus 1. Yeah. So only if feasible design, then I can move on. So I should move on after I do the plotting. Right? Until I got the 10th design, so I is larger, equals to 10. So equal sign. If when I equals to 11, then I stop. Okay, let's see what's gonna happen. Okay. Yeah. Okay. 1, 2. So I have 9 designs, but from here you can see it's very difficult to generate a design that is lying on the equality constraint. It's not easy. It's not easy. Trying to figure out why you never have design from outside. Let me see. Okay. I only accept possible values. So I should say the absolute value of plugging into the equality constraint. If it's larger than 0.1, then infeasible. Earlier, I only accept possible. I only accept one side of the design, not the other side. So maybe this is better. Yep. But very slow. Why is that? Because it keeps on generating bad design. It doesn't lie on the constraint. So it is still busy. So maybe it's generating a lot of bad designs. So I guess I should open up the tolerance, maybe 0.5. Otherwise, we are randomly generating too many poor designs. Okay. I'm curious about how many poor design we generated. So whenever there is a bad design, I will do a poor design or just an invisible counter. Okay, just to curiosity, if there's an invisible design, I will just count how many invisible design I have. Because you need to manage your programming. If your coding is spending a lot of time generating bad designs, you may want to change some of your parameters. I guess a lot, thousands of them. So 822. MATLAB spent 822 random, actually totally 832 random generated points. Out of 832, only 10 feasible. 822 invisible. So this is purely because you have a equality constraint that is on a line, on a curve. So you want the random generation to just luckily fall onto that curve. That requires a lot of luck. Okay? So I guess that's fine for now. Let's continue. But later on, maybe we can try to solve. Actually, I want to eliminate the equality constraint just for now, so we can see more usual GA process. So over here, I will turn off the plotting for the equality, and also I will turn off the checking for equality. Okay, I think it will be much easier. So from here, let me just double check. Okay, so you can see GA was able to find 10 possible points in the feasible space. It only generates 14 invisible designs. So 14 are outside, 10 are inside. Okay, so that's more like a effective random generation. Next, I want to check the fitness. Okay, so over here, fitness value. So for each design, because we are minimizing, so I will think if the value is smaller the better, right? So I will treat smaller fitness as better design. And since I have, I know for my problem, function value equals to 0 is the smallest possible smallest function value is 0. Okay, so I may need to know what is the largest. So f max would be substituting. I may need to compute this after I define the zone. substituting f and then x1, x2 and use zone 2 and 4 to plug in. Then I know what's the largest function value. So this is only good for this specific simple problem. So I know the function range. Possible minimum f is 0. Possible maximum f is after I plug in this. So over here, my fitness would be, I'm gonna call it fit. The ith one equals to substituting function value x1 and x2 and the current design. So this will be my function value, and then divided by max function value. So at the end, it will become a value in the interval of 0 and 1, and smaller, better, right? If I do that, let me try to do this. Oh, this is a while loop, so I have to do it outside. Or no, actually here. I should do it here. Fitness has to be done here, right? So my fitness value is being computed inside this check. Okay, do it again. Yeah. So let's take a look at all the fitness value. Oh, what did I call it? Oh, fit. So they are not scalar. So let me evaluate. Run it again. So let me turn off the warning. Warning off. Okay. So let's check the fitness. So I have 10 different fitness. How come the first one is 0? First one is 0. It's weird.谁？我在上。I should say I equals to 1 at the beginning. I forget to do that. Okay, so fit. Yep. So now I have 10 fitness values. So they are different function. They basically ranges within 0 and 1. Okay, so the smaller is better. Smaller the better. Now I want to, like I said, I want to do selection. So here I'm gonna do selection. I will have a sum of fitness value. So basically, sum of it. Okay? And I'm gonna use a for loop. One to pop, and the probability of selection equals to its own fit divided by sum of fit, just like what I mentioned. Okay? So let's try this. See what's gonna happen. So I should have a probability of, let's take a look at the fit. These are the 10 fitness values and the probability of being selected. Wrong. Here I should put an I here. Run the code again. Here are the fitness probability of selection. So over here you can see I did it wrong because here if I have a probability proportional to the fitness value, then lower fitness means lower probability. But in my case, lower fitness is better. I said lower the better, right? So what I can do here is I can use 1 minus my fitness or 1 minus my probability. It depends on what you want to do. So maybe I will say 1 minus the fitness. Or 1 minus, I'll do 1 minus fitness on the top. So now, larger the better. Larger the better. Still, fitness value within 0 and 1, but now larger the better. So run the code again. You can see fitness, 10 fitness value, selection or probability. So which one is the largest? This one is 0.84. So this chromosome has the highest fitness. So among their selection probability, it has the highest probability to be selected. So there is a 17% this chromosome should be selected. Okay? So what you're gonna do next is to sort, to line up, sort their fitness, maybe from the largest to the smallest, and then line up their probability. So what you can do is to or you don't sort them, you just okay, maybe you don't sort them. So here you are going to create a for loop again. One to pop, because at the end you still need 10 chromosomes. Every time you have a random selection number, so I'm gonna say rand 1, just one random number. Okay, so we already have a probability line up. If you sum the probability of selection, it will equals to 1, right? So now I will randomly generate a number. Let's say 0.1. Is it larger than this? Yes. That means that random number doesn't fall in this area. So I will minus that random number 0.1 minus this. The remainder, check if it's within this interval. If yes, okay, then this one is selected. So you can keep on checking the random number, see which interval it's falling. Oh, it's falling here, then I will pick up that one. Okay, so that would be an easy way to to know where the random number falls into. So here I create this random selection number, and then I will say for j goes from 1 to the pop again, and you will use remainder equals to the random selection minus that jth probability. So probability is here, the jth one, minus that. So if the remainder is positive, you keep going. So remainder equals to this, right? So you should say, oh, you don't need this. You just use the random select. So the random select equals to your original random number minus the jth probability. See if this is positive. See if this is positive or negative. So if this becomes negative, that means that particular position is the selected one. So in that case, jth one is selected. So over here, this means jth chromosome should be selected. Right? Yes. So we will have chromosome. Originally we call chromosome. So we'll say it's a selected chromosome. Ith equals to the jth. So chromosome J. It's like this. But you need to do this. So you keep on doing this. You will end up with 10 selected chromosomes. So let's take a look. Chromosome select. Oh, something must be wrong. Minus the jth. Okay. After you do this, you need to break. Otherwise, something's wrong. Let me pause here. Okay. So now, random number. So J fourth. Okay. Step. Okay. The next one, I randomly generate a number. This is 0.77. 0.77 minus this becomes smaller but positive, not yet. And keep on minusing, not yet. Okay, so yes, the J was 8th. Okay, so different chromosome will be selected. So let me show you at the end. So originally, let's take a look at the selected chromosome. Do we have the exact same one? It's hard to read. Maybe I will print the number as well. So I will say here, basically J. Okay, run the code again. So 92, or I just keep it as a memory, so we can easily check. I will say ID of selected, I equals to J. So later on we can come back and see which one has been selected. Okay, run the code. So the ID of selected 4A blah 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 blah. Okay, so you can see 4 has been selected 4 times. 7 has been selected 3 times. And let's see why. Let's check on the fitness. The fourth one, is it having a fourth one, or let's check on the probability. Probability. Fourth one indeed has a pretty good probability, 172. And seventh, also pretty high probability. But for some reason, the first one actually is having a good fitness value, also high probability, but this time it's just unlucky. The first one was not only being selected once. So this is all random process. We can try it again. And let's check on the ID of the selected. Let's check on the fitness value. And let's check on the probability of selection. So this time the largest is the last one, 10th. The probability of selected is 18%. 10th being selected 3 times. Okay? 7 twice, 1 twice, 5 twice. So the good ones being selected multiple times. But take a look at the fourth chromosome. Its fitness is bad. Its probability of selection is poor. However, it's being selected. It's all because of the random process. Okay? So that's the idea. Now we have the new selected chromosome. So we can then perform crossover. For the crossover, I will randomly pick up. Should I randomly pick up? Because in the 10 chromosome, if I choose every 2, the total combination is a lot. So I should randomly pick up 2 and decide whether they will have crossover. And after crossover, they never recover back to its origin. So this is what I'm going to do. Before I do that, I want to highlight the selected chromosome. Yeah. Let's highlight the selected chromosome. So let's plot out which chromosome being selected. So we need to know we need to map the chromosome back to X. So here, we can do this here. So again, we don't need the max decimal. We just do the mapping. So here, chromosome select. Chromosome select. Okay? And here I'm gonna call it chromosome select X and chromosome select X. So this is how we map it back to X. And then we will do the plotting here. We will do the plotting. Select. But when we plot out the selected one, let's change the color. Change it to red. Okay? So let's take a look. Oh? Oh, why? Hold on. Huh? Oh, because I break here, sorry. I should break at the end. That's why. Okay. Do it again. So here, the best ones were selected. So from here you can see those are the one that is closer to optimal, but some of the bad one being selected. I bet those one being selected multiple times. Let's try again. Okay, so these are the good ones. This is a bad one, but the red one are the one being selected. Now, crossover. So within crossover, out of the selected one, we will randomly pick up 2. So for I goes 1 to pop, and for we only do 10 times. We just randomly perform crossover 10 times. How about that? Okay? So we don't, if we go through all the possible combinations, so 10 out of 2, that would be 10 times 9 divided by 2. That means we will be go through 45 possible combination of selecting 2 chromosomes. So I think that would be a lot. So I choose to just randomly pick up 10 possible combination and see if we perform crossover between those randomly chosen 2 chromosomes. So I will just use rand and create 2 numbers. So after I create 2 numbers, I need to map it to I will multiply by 10, actually my population number, and then round it. So, but if that's happening, I may have 0 because I want to randomly pick up 2 index from 1 to 10. From 1 to 10, not 0 to 10. So when I randomly generate 2 values, it's a random number from 0 to 1. And if I multiply by 10, it's random number 0 to 10. So I can do seeding of them, not rounding. Then seeding. If I do seeding, Let me show you. It will be two random numbers. Seal. One by two. 1 and 2. So, two random numbers, if I use rounding, sometimes I will get 0. If you are unlucky. Like this one, you have 4 and 0. So I should use seeding. I will always get values from 1 to 10. Do I get 10? Yeah, sometimes 10, right? Okay, so seeding. So the ID for crossover. But sometimes those two ID would be the same. So if ID crossover 1 equals to the second, I need to do it again. Then, or I say while this is happening, then repeat. Just in case the two random numbers are the same. I just repeat this. So whenever it's not the same, the two random IDs will be chosen. Once I do that, I will use a for loop. J goes 1 to pop -1. Not population, the bits. Total bits would be, where did I define bits? Bits. Totally I have 16 bits. So 2 times, this is 16 bits. But 16 bits has 15 gaps, right? Or I can, so 16 bits has 15 gaps. So for the gap, from the first gap to the 15th gap, every time I will randomly generate a pointer. So I will again generate a random number. So if this random number is smaller than my crossover rate, so here I'm gonna define crossover rate. I'm gonna say 50%. So if this is happening, then swap. So at the jth gap, I will say the selected chromosome, the first one, the chosen ID, and jth gap. So J may be 1, so J plus 1, until the end will be swapped with its neighboring chromosome. So second one. So these two needs to be swapped. So I will say, let me keep a memory. Chromosome memory equals to this. So before I do everything, I should always have a empty chromosome memory. So before I do this, I always have a empty chromosome memory. So my chromosome memory will be just keep in mind what the body looks like, and my chromosome, I should have memory 1 and memory 2, right? So this will be my first part of the memory and second part of the memory. Okay. Then do the swapping. So the first one now U equals to the second memory. And the second one now U equals to the first memory. Yeah, that's one way to swap, right? So when this happens, you can break because you only do crossover once. I need to make sure I'm coding this right. So let's run the code. Yeah. Something's wrong here. Second. Okay. Now let's take a look at what are the chromosome IDs. No, this is not what I want. So 1 and 2 here, sorry. So do it again. So the crossover ID. So the fourth one and the second one needs to be swapped. So let's take a look at what's before. So the fourth one, oh, not X, wrong, not X. Just select it, no X. Yep. Okay, so there was a typo. Do it again. Run the code. Okay, now the random ID 6 and 8, and if I check their chromosome 6 and 8, so originally their chromosome looked like this, 6 and 8. Now I go through random number. So now J is 1. Oh, so I guess my crossover rate is quite high. Easily crossover. Is it a good thing? I think I should use a lower, just 0.3. Otherwise, it's always doing crossover at the front of the bits, not the tail of the bits. So I don't want my crossover to be too high. Okay, now this time, okay, second bit. Okay, second bit. Or sometimes people just randomly find the crossover position. Yeah, because the way I'm designing this, it's very possible you are taking the crossover in the first couple bits. The tail of the chromosome never perform crossover. So I guess in my case, I just lower, make it 0.2. I don't want J now is 10th. Okay, now I think if it's possible to move on to the 10th gap and perform crossover, that's a better even probability of crossover for me. So here IDs will be 9th and 3rd. So let's take a look at the chromosome 9th and the crossover chromosome 3rd. So it's at 10th at 10th gap, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th. 10th cutting right here, so their tail should be exchanged. So let's take a look, the coding. If I perform this, and then check on 9th and 3rd again, you can see the 9th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for the 9th chromosome, its tail has been swapped with the 3rd. So the tail is swapped. Okay? So now this is performing exactly what I'm looking for. So that would be one possible crossover. And I will be doing this 10 times. So 10 chromosomes will be swapped. Okay, and whenever it's swapped, some of the body is swapped, it never swap back. So that particular chromosome disappear because some part of its body swap with some others. Okay? Then I'm gonna perform mutation. So for the mutation, similar codes, but mutation rate, I would say much lower, maybe 5%. Okay? So for the mutation, I will check on every chromosome. Every chromosome. I only want a pretty low rate of mutation. I don't want every chromosome to mutate. So for every chromosome, I will go through from its first bit to the last bit. So 2 times the bit. Okay? Go through the first bit to the last bit. If a random number that is smaller than the mutation rate, that means that particular bit needs to be mutated. So for that particular chromosome with the jth bit, so ith chromosome, jth bit has to be swapped to 0 or 1. So I will say if this one equals to 0, then switch to 1. Else, switch to 0. That's it. And after the switching, break. Because I only want one chromosome at most being mutated once at 1 bit. Okay, so let's pause right here just to check whether the mutation code was right. So we don't worry about crossover. Okay, mutation. Here we are dealing with the first chromosome and right at the 11th position. So let's take a look at the first chromosome. This is the first chromosome. So let's run the code. Step. Okay, and check on its chromosome again. So the 11th position, 5, 10. Originally this was 0, now change to 1. That's it. That's only change. Okay? So after mutation, some mutation happens, some mutation may not happen. But at the end, we need to do feasibility check again. Feasibility and fitness. Feasibility, fitness, and so-called elitism. Keeping the elite. It's okay. So now, feasibility check, I had the code already. Feasibility check was here. Right? Just do all these again. So for I goes from 1 to population, do all these. Okay? But right here, you are using the I need to evaluate the x value, map to x. So after all these, I need to map everything to x. So these will be the final x value for the final chromosome. Okay? And then feasibility here. Okay, feasibility here. But selected x. Okay. The feasible flag, I should put it here. For each design, initially you assume it's feasible, and then check if it's feasible. If not, change it to 0. If it remains feasible, okay, good. Plot it out. So this time we are going to plot out in a different shape. Let's use a cross and the blue color. So the blue cross will be the crossover mutated design. Okay? And the fitness, let me just use select the ith one. Okay, here selected x. Okay, now we can still keep on checking the infeasible. We don't have infeasible counter because we don't random generate new design anymore. We don't mind if the mutated design is not feasible. If not feasible, that's fine. Okay? So once we do that, let's check line by line. Okay? So here converts everything to x coordinate. Okay? Feasible check on the constraints, plug in the points. Is it feasible? Okay, feasible, plot. Okay, now let's take a look. Okay, so there's a new design here. It may not be super good. And then check its feasibility 0.58. Okay? And let's continue to do the same. You end up with, you can see, originally there were black circles. There are 10 random designs. Some of them become red circle. They are the selected ones. And out of the selected ones, some experience so-called crossover, some experience mutations, so new designs happens. So there are some blue crosses, but there may not be 10 of them. So you can take a look at the fitness. I should the fitness of the selected. You can see the fourth one is 0. That means the fourth one is infeasible, and the last one disappeared. There's no last one. That means we didn't evaluate last one. Last one is infeasible. So at the end, we end up with 8 designs. So we're going to keep the best one. So based on my coding right now, I guess what I can do is I can keep one best design from selection, and I can keep one best design from mutation. So let's do that. So after selection here, I'm gonna choose, so the best out of selection ID is, so basically the max of, not from selection, from generation. Max of fit. So the best selection, and I will have a memory. So best chromosome 1 would be that particular ID. So chromosome and best ID. I will keep a memory of it. Okay, and after all the mutation and things, I will do this here. Best mutation ID after mutation. Max of the fit select. And then best chromosome, the second best chromosome, I will pick up from the best mutation ID. Yeah, that's it. So I will end up with 2 best chromosomes. So let's run the code. Something's wrong. Best. Sorry, not the. I should say something like this. Yeah. If you want the ID, this is how you get the ID. Okay? Because max operation has 2 outputs. Second output is the ID. Okay, so let's take a look at the best chromosome. I have 2 of them. Okay? So maybe I can plot out those 2. So I should also keep a memory of their position. So best chromosome X equals to here, just bracket X, okay? And here, second one would be the one after mutation. Chromosome select. Here should be chromosome select. Yep, should be like this. Okay, run the code. And then we should, just in case, plot out where they are, since I have their X coordinate. So let me just plot out where they are. So for loop, 1 to 2 of them. Just plot out the very best, 2 very best. This time, I'm gonna use a different line format, a plotting format. Maybe a square, and magenta. It's like a pink color, but marker size larger, 8. Do it. Okay, from here you can see these are the 2. The pink square are the 2 best chromosome. So this one is the one being mutated. And how about this one? This one is the one that was originally a red circle. Let me make it larger. 12. Okay, so over here, this one is the one originally being random generated and the overall best out of the random generation. And this is the one out of the GA process. So these two will be the elite. I will send to the next generation. So here I need to move on to do next generation. So I need a big while loop. And or I will just say for gen equals to 1 to max gen. Yeah. So I just do this max gen. So this whole thing tab. So we will perform this 100 times. So for the random generation, if gen equals to 1, then you can do this. Or I should say, if gen larger than 1, that means we are in the next round. Okay, so our chromosome, the first one and the second one, equals to the best. Two of them. And also later on when I do the while loop, I can start with the third, right? I can start from third, because I already have the first and second. First and second are the two best from the previous. I start from the third. But you need to keep in mind, you need to also compute for the X. We already did the best chromosome X. We did that already. So you need to pass those values to chromosome X as well. Their feasibility check, their fitness. I didn't keep a memory of the fitness. Let me do that. So when I compute for the best, I should also best fit first equals to fitness and best selection ID. Yes, and then second one would be best mutation ID here. But the fitness is called best selection. Yep. So I will have two fitness value. I directly send them to here. So the first two equals to the one we had from the previous iteration. Should be right. Should be right. Okay. I'm not sure, so let's run the code. Okay, so in the first iteration, because generation is 1, so we don't do this. We just do what we did earlier. Okay, so one iteration has been done. And then in the next iteration, because gen equals to 1, so chromosome first and second will be replaced by the best. and also their fitness will be replaced starting from the third. So over here we will random generate the third one. Yeah, so continue. So over here, you see a new pink box. The goal is, after 100 iteration, let's see if the pink box move toward the optimal. So we can keep on monitoring. Something must be wrong. How come there's a pink box here? But you kind of get the idea. I need to debug a little bit. But you can see that overall best is always at the bottom because that's where the solution is. And now the process is slow because we are always plotting out the results. Okay, it's taking a while. Let me pause it. I want to show you something called the history of the fitness value. So after every generation, I want to make a drawing. I want to show how our best overall fitness drops. Increases. Right now, higher the better. So I'm gonna call whatever I plotted as figure 1. And I'm gonna make a figure 2. So I think I can do it here. Figure 2. And the figure 2 would be plot and plot out the generation number and also the max fitness. And I'm gonna just draw a circle and blue, okay, something like this, and hold on. So every generation I will plot out our best fitness value and see how it look like. But when I go back here, I need to switch back to figure 1. Okay. Figure. Something's wrong. What? Hold on. Sorry. Wrong again. Let's pause and take a look at the figure 2. Some plot was sent to figure 2. Why is that? Figure 1 here. Figure 2 here. Those points were plotted in the wrong figure. Figure 1 here. Figure 1 here. Do I need to specify figure 1 all the time? I don't think so. Anyway, where do I do the plotting? Okay. Just remind MATLAB plotting in figure 1. Okay. Okay. Only here is figure 2. Right before we evolve to the next generation. Okay. This should be alright. Let's try just how many generation? Maybe 20 generation. How about this? Okay. No. How come it mutates, but I don't know what happened. How come it generate poor design, infeasible design? So something must be wrong in my coding. Why is it not finished? Next generation. Finish, right? Okay, hold on. Taking too long. But if you take a look at it's always the same one. It's very possible that. Okay, sorry, it's out of time. I cannot continue. I don't want to occupy your lunchtime. So there must be some bug here and there, but you kind of get the idea. GA is a kind of coding like this. Randomly search, try to find random solutions in the feasible space, pick up the good ones, and try to use crossover and mutation to generate new movement. And it really depends on how you allow movement. And over here, my code, for some reason, moved to the infeasible space. So some part of my code must be wrong. But at least you can see, among all these randomly generated design points, actually GA explored the space. It spent a lot of time exploring. So it's not like a gradient base. It's quite effective. It just knows where to go. So if you are solving a problem that is continuous, if you can solve it by gradient-based approach, it will be more effective. GA usually is utilized for this pre-selection because for some cases you just cannot have continuous decision. For example, number of teeth of a gear, you cannot have 1.5 teeth, right? Teeth. So that's basically the situation. Okay, so yeah, that I will go back and debug and then send this code to you. And next week is our progress report. So this week we don't have any exam anymore. Please work with your teammate, work on your progress. So last time I gave you some suggestions. It's okay to modify your topic. It's okay to change the selection of your method. So, but if I gave you a suggestion or question, I think that's important questions. So please make modifications based on my suggestions. So next time, it's similar style like the proposal, but I think you should have some progress on your project. Okay, and for whoever wants to do makeup for the exam 1, I think we can use this week. So I will send you Facebook message or email and arrange time with you. You can go to my lab and then do the makeup for exam 1. I'm not finished with the solution grading of exam 2. I will try to finish in this week. So we will determine whether we need makeup for exam 2. Okay? That's it. If you have questions, you can stay here. Okay, see you, bye-bye.